Previous lecture we have discussed about the star connected three-phase system. So let's try to solve some numerical on star connected three-phase system. So the first question is, a three-phase load consists of three similar inductive coils of resistance 50 ohms and inductance zero point 0.3 Henry each. The supply voltage is 415 volt 50 Hz. So calculate the line current, power factor, total power, total volt ampere when the load is star connected. So let's see the solution. Here in this question, first of all, the values are given as the line voltage as 415 volt. The frequency is 50 Hz. The resistance here given as 50 ohms and the inductance is 0.3 Henry. So these are the value given. So first of all, we can calculate the phase voltage. As we know that in a star connected system, the phase voltage is line voltage upon root 3. So it will be 415 upon root 3, and that is 239.6 volt. Now find the value of XL. Remember here it is the inductive reactance per phase. It is 2 pi FL, where frequency is 50 and the L is 0.3. So finally we'll get the value of XL as 94.25 ohms, and the resistance of the phase is resistance per phase is 50. Next, impedance per phase, that will be square root of R phase square plus XL per phase square. So the values are 50 square plus XL we have calculated, it is 94.25 square, and after solving this we'll get the impedance as 106.69 ohms. It is the impedance per phase. The phase current is the phase voltage upon the phase impedance, where the phase voltage is 239.6 and the phase impedance is 106.69. So the value will be 2.246 ampere. As we know that in a star connected system, the phase current and the line currents are same. So the line current will be equal to the phase current, and it will be 2.246 ampere. This is the value of line current. Now the power factor of the circuit, cos phi, and it is the ratio of resistance to impedance, where the resistance is 50 and the impedance is 106.69. So we'll get the power factor cos phi as 0.46 0.78, and it will be lagging. As in the question it is given that in each phase there is a resistance and there is an inductance. That means the circuit is resistive inductive. And as the circuit is resistive inductive, so the current will lag the voltage and hence the power factor will be lagging in nature. Next, the power. The total power means the active power. So P can be written as root 3 VL IL cos phi. We can use 3 B phase I phase cos phi also. So it is root 3 into the line voltage is 415. The line current is 2.246 and the power factor is 0.4678. So after calculation, we'll get the active power is 755.23 watts. So this is the active power. In the question, the total volt ampere is also we have to calculate. Total volt ampere means the apparent power. As the unit of the apparent power is volt ampere, so the total volt ampere means the apparent power, and that is root 3 VLIL. So here again the VL is 415 and the IL is 2.246, and after solving we'll get the apparent power as 1614.43 VA, that is volt ampere. So this is a complete solution. The next question is a balanced three-phase star-connected load has an impedance of 5 minus J10 ohms per phase and is supplied from a balanced three-phase 400 volt 50 Hz supply. Calculate the phase voltage, line current, power factor, active, reactive and apparent power. So let's see the solution. Here the impedance per phase is 5 minus J10. That is the resistive capacitive circuit. We have already seen that in complex notation. Minus reactance means it is a capacitive reactance. That means the circuit is a resistive capacitive circuit. The impedance per phase can be written as 5 minus J10, and if you want to convert it to the polar form it will be 11.18 angle minus 63.4 degree. This is the impedance per phase. VL is here 400 given. So the phase voltage will be VL by root 3 as in a star connected system. Phase voltage is line voltage upon root 3. So it is 400 upon root 3 and the value will be 230.94 volts. So the phase current, as we know, it is the phase voltage upon phase impedance. So the phase voltage is 230.94 upon impedance. Here we will consider only the magnitude of the impedance, that is 11.18, and the value will be 20.66 ampere. We also know that the line current and the phase current is same in case of star connected system. So the line current is also 20.66 ampere. In the impedance, in the polar format of the impedance, we have got the phase angle is 63.4 degree. Remember one thing, the impedance phase angle is also the phase angle of the circuit. That means this is also considered as a power factor angle, that is phi. Here the phi is 63.4 degree, but it is leading because it is a resistive capacitive circuit that we can understand from the negative reactance. This is a capacitive reactance. Hence, the phase angle will be considered as a leading. Leading means that the phase current will lead the phase voltage by this angle of phi, and it is applicable for all the phases. In each and every phase, the corresponding phase current will lead the corresponding phase voltage by the angle of phi, and here the phi is 63.4 degree. Therefore, the power factor of the circuit will be cos phi, that is cos 63.4 degree, and its value is 0.4478 leading. Now the active power. There are different type of formula for active power. We know that it is 3 V phase I phase cos phi, it is root 3 VLIL cos phi, as well as it can be also calculated by using 3 I phase square into R phase formula. It is also used to calculate the active power. So here if we use this formula, so the I phase is 20.066 square into R phase. R means the resistance of the circuit, that is 5. So the active power value will be 6409 watt, or we can also write 6.409 kilowatt. Next is the reactive power 2. It is root 3 VL IL sin phi. That is the reactive power of a three-phase circuit. So VL is 400, IL is 20.66, and sine of phase angle, that is 63.4 degree. And after calculation, the value here will be 12798.63 volt ampere reactive or var, and it can be also written as 12.8 kVAR. That can be also written. Finally, the apparent power S, it is root 3 VL IL, or it can be written as 3 V phase I phase. So let's use this formula. The phase voltage is 230.94 and the phase current is 20.66, and finally we'll get 14,313.67 VA, or 14.31 kVA. So this is a complete solution for this question. Here the next question is, the third question is, a balanced three-phase star-connected load of 18 kilowatt taking a leading current of 60 ampere when connected across a three-phase 440 volt 50 Hz supply. So find the nature and values of the load. Let's see the solution. In this question, the total power is given as 18 kilowatt, or it can be written as 18,000 watt. The voltage, that is the line voltage, is 440 volt. Remember one thing, when in the numerical questions the voltage is given for three-phase circuit, it is always line voltage. The voltage will be always considered as a line voltage unless it is mentioned otherwise. And the frequency here is 50 Hertz. Now, in this question, the current is also given as 60 ampere. And again, the current that is given in the question will be considered as a line current. But we know that in a star connected system, the line current and the phase current are same. So the line current as well as the phase current will be 60 ampere. So it is a very important point. Always remember, when the voltage and currents are given in the question, it is always considered as a line values. Other values, for example, resistance, inductance, capacitance, uh, inductive reactance, capacitive reactance, or impedance, or power factor, if these values are given in the question, it will be considered as the phase values. So during numerical questions, we have to remember these points. Now, in this question, it is given that the current is leading, and the current becomes leading for a resistive capacitive circuit. Therefore, as the current is leading, then we can conclude the nature of the load per phase is RC type, that we can identify from this line, that is the leading current. So here we have to find the value of R and C. Now we know that the power is root 3 VL IL cos phi, that we know. So here put the values. We know the value of power, that is 18,000 watt. We know the line voltage, that is 440, and the line current is 60. And the power factor is unknown, so we can calculate the power factor from this relation. It will be 18,000 upon root 3 into 440 into 60. And after calculation, we will get the power factor as 0.3937, and it will be leading because the circuit is resistive capacity that we have already identified. Hence, the power factor will also be leading in nature. Next is the resistance per phase. Uh, One more thing, we can here find the value of impedance per phase also. That is the Z phase. And the Z phase will be V phase upon I phase. V phase means it will be line voltage upon root 3. And I phase is equal to IL. So here it will be 440 upon root 3 by the current is 60. So it will be 4.234 ohms. That is the impedance per phase of the load. Now the resistance per phase. From the impedance triangle, we know that the resistance is R is equal to Z cos phi. So here it will be 4.234 and the cos phi we have calculated is 0.3937, and after solving the value of resistance will be 1.667 ohms. That is the resistance per phase. The capacitive reactance can be calculated by using the formula Z phase square minus R phase square, because we know that the impedance of a capacitive circuit is square root of R square plus X square, that we already seen in the RC circuit analysis. So from this relation we can write Xc equal to square root of Z phase square minus R phase square. So put the values here. It is 4.234 square minus 1.667 square. So after calculation, the value of the X will be 3.892 ohms. So this is the value of Xc, and we know that the Xc is equal to 1 upon 2 pi Fc. So here we can write 1 upon 2 pi Fc is equal to 3.892, or we can write C is equal to 1 upon 2 pi F into 3.892. So it is 2 pi into F, that is 50, into 3.892, and after simplification the value will be 817.86 into 10 to the power minus 6 farad. So finally the value of C will be 817.86 microfarad. So this is the resistance per phase of the load, and this is the capacitance per phase of the load. Now the fourth question. Three identical coils are connected in star. Line current kilowatt and kVA input are 15 ampere, 11 kilowatt and 15 kVA respectively, when connected to a three-phase AC supply. To determine the line and phase voltage of the supply, kVAR input, power factor and impedance of the coil in complex form. So let's see the solution. First of all, in this question, the values that are given are line current. It is 15 ampere, and as it is the star connected system, so the line current is also equal to the phase current. Next, the kilowatt is given. Kilowatt means the active power is given. So P is equal to 11 kilowatt, and kVA is given. kVA means it is a unit of the apparent power. That means the value of AC is given here and is 15 kVA. So these are the values given in the question. Now we know that S is equal to root 3 VL into IL. or we can write VL is equal to S upon root 3 into IL. Here S is 15 kVA, so it will be converted to VA. So 15 into 1000, and the line current is given as 15 amperes. It is 15. So the value of VL we will get as 577.35 volts, and the phase voltage is the line voltage upon root 3 in star connection. It will be 577.35 upon root 3. So we'll get the phase voltage as 333.33 volts. So this is the phase voltage and this is the line voltage. Now the reactive power, here you have to calculate the kVAR input, that means the reactive power Q. And from the power triangle we know that Q can be written as square root of S square minus P square, because we already know that the apparent power can be written as square root of P square plus Q square, that is the active power square plus reactive power square. So from there we can write Q equal to this. So now put the values of S and P. So it is 15 square minus 11 square. So the value of Q will be 10.2 kVAR. So this is the value of reactive power. Next is the power factor. We know that the power factor is the ratio of active power to the apparent power. And this formula is also applicable here in three-phase circuit also. So the active power is 11 kV and the apparent power is 15 kVA. So finally the power factor will be 0.733 lagging. It is lagging because in the question it is given that three identical coils, and coil is always the RL type circuit, and for resistive inductive circuit current always lag the voltage, therefore the power factor will also be lagging. From here we can find the value of phi, that will be cos inverse 0.733. It will be 42.83 degree. That is the phase angle. And impedance per phase is voltage per phase upon current per phase. The voltage per phase we have calculated 330.33, and the phase current is given in the question, that is 15. So here it will be 22.22 ohms. This is the phase impedance. Therefore, the impedance can be written in the form of complex number as 22.22 angle 42.83 degree. Here the angle will be positive because it is a resistive inductive side. The angle is positive because it is RL circuit. For RC circuit the angle should be negative, and for RL circuit the angle is positive. And now if we want to convert it to the rectangular format, it will be 16.3 plus J 15.1 ohms. In the rectangular format, 16.3 is the resistance per phase and 15.1 is the inductive reactance per phase. And if we want, we can find the value of L also, because we know that it is XL equal to 2 pi FL, and if the frequency was given in the question, we can also find the value of L. That is the complete solution.